Now we're going to turn our attention to a pair of reaction types called substitution and elimination. Each of these types of reactions can happen in two different ways. So there's two versions of substitution and two versions of elimination. That gives us four possible pathways or four possible mechanisms. So our goal with this is to be able to assess the conditions of the reaction and to decide which of those four pathways is the most likely. Now, what do we mean by conditions? That's just how you're setting up the reaction, what's involved in the reaction. So what solvent are you using? What reagents are you using? What temperature are you running the reaction at? These are all examples of what we would consider conditions. The problem with this is that some of these pathways, these four pathways, compete with each other. And what that means is that the conditions that favor one pathway also favor another pathway, and so you're going to get multiple products. So the trick is to become familiar with the nature of the chemicals that you're going to be seeing over and over again. So that's not only the substrates, but the reagents that we're using to convert our substrates into product. So if you become familiar with these, you can make an accurate assessment, given a set of conditions, given a set of reagents, as to what the most likely thing is that that combination is going to do. Think about this kind of as a medical diagnosis. And a patient comes to you and they have a set of symptoms. And you weigh that against what you know about what the likely disease that that person has may be. To start out with this, before we get into an overview of substitution and elimination, let's look at some information, some of which we've seen before, so we'll review that, but some information that's going to help you as you get used to looking at chemicals and understanding what their nature is and what they are most likely to do in particular situations. So this first table up at the top, on the reference tables page, helpful Bronsted acid-base information. So we developed this table together in the acid-base section. And so you should have this memorized. So one place to start, if you haven't done this already, is to make sure that you know the strong acids. So the ones from general chemistry, HCl, HBr, HI, sulfuric and nitric acids, as well as TSOH, which is tosic acid. So that's a strong acid that's used by organic chemists. So tosic acid. And also to remember that because these are strong acids, all of their conjugate bases are weak. Now, another point on this table that's important for you to focus in on is this right here. So RO minus, you need to be able to recognize RO minus when you see it. That refers to an alkoxide ion. So where might you see these? Well, three that you're going to see over and over again would be this guy. This is an RO minus or an alkoxide ion. This is the methoxide ion. Or you might see this one. So this is the 2-carbon alkoxide ion. This is ethoxide. And then a third one that you'll see is this guy. This is called tert butoxide. So what you should know about these, besides the fact that they're all conjugate bases of alcohols, is that they are all strongly basic. So that's important to remember. That's part of their nature, if you will. So these are commonly encountered alkoxide ions. Another thing that you're going to be seeing a lot of are nucleophiles. Now, this table, frequently encountered nucleophiles, has the nucleophiles arranged in categories from very good to fair to weak to very weak. And what these categories are reflecting are what we call their nucleophilicity, or the nucleophilicity of these different chemical species. Nucleophilicity is just a measure of how fast something reacts as a nucleophile. So I'll just abbreviate nucleophile as nuc. So what this means is that something, for example, in the very good category, like I minus, iodide ion, is a better nucleophile, meaning it reacts faster than something in the fair category, for example, like the fluoride ion. So we're going to see lots of nucleophiles. And finally, the other thing that we're going to see a lot that you'll need to become familiar with is a thing called the leaving group. So all of these reactions that we're going to be studying in this section of notes, whether they're substitution or elimination reactions, all of them have to have leaving groups. And the leaving groups have to be things that can actually leave. So there's good leaving groups and not so good leaving groups. So things that fall into the good leaving group category be things like iodide ion, bromide ion, chloride ion, something called OTS, which we'll see later in this section. That's called the tosylate ion, and we'll look at the details of that when we get there. Water and alcohols, and carboxylate ions, so conjugate bases of carboxylic acids. What these all have in common is that they are all weak bases. So if something is a good leaving group in a substitution or elimination reaction, it's going to be weakly basic. Now, if we go to the other side of this, the poor leaving groups, those include things like hydroxide ions, alkoxide ions, fluoride ions, and carbanions and hydride. Now, most of these are strong bases. The exception is the fluoride ion. So we'll put that. These are mostly strong bases, except for this guy, which is a weak base, but a little bit on the borderline. Okay, so it's on the strong end of being a weak base. Let's put it that way. So if you know acid and base strengths, specifically for what we're talking about right now with the leaving groups, base strengths, if you understand base strengths, again, getting used to the nature of some of these chemicals, that's going to help you a lot. What we can say as a general guideline with the leaving groups is that the weaker something is as a base, the better it is as a leaving group. So weaker bases make better leaving groups. Okay, now let's turn our attention to an overview of the 4 types so you can get the information, the basic information about each of the types in one place, and then we'll go from there. So in all of these reactions, just like with the addition reactions that we looked at, there's going to be some kind of substrate or starting material. That is the organic molecule that's undergoing the reaction. So the reaction to turn it into something else, that would be the product. In a substitution reaction, regardless of which variety of substitution you have, one part of your substrate is going to leave during the reaction at some point, and it's going to get replaced by something else. So the thing that leaves is the leaving group, and the thing that replaces it is the nucleophile. So a nucleophile replaces a leaving group. So a substitution can happen either through a stepwise mechanism. That's going to involve a carbocation, so we're familiar with those already. That's helpful. That's called SN1. Or by a concerted mechanism, and that's called SN2. So let's look at details about each of these pathways, as well as a little more information about what stepwise and concerted means. So the stepwise variety of this, of substitution, again, is called SN1. And what we mean by stepwise is that the reaction happens in a series of elementary steps. So it happens in a series of elementary mechanistic steps. By contrast, a concerted version of a substitution reaction is referred to as SN2. So that's its mechanistic label. And this happens all at once, meaning that the reaction mechanism has only one elementary step. Now, SN2, we've seen already. We saw it when, for example, we opened a bromonium ion with a bromide ion in an addition reaction. Things like this. So let's start with SN2 because we already have a little bit of information about it. Okay, so I'm going to give you a set of conditions. And then we're going to start labeling things in the way that you're going to get used to labeling them as you assess conditions of reactions like these going forward. So the thing on the far left, which is ethyl bromide, this is our substrate. Now, in a substitution reaction, the substrate is reacting with a nucleophile. The nucleophile is over here above the arrow. It's the cyanide ion. So Cn minus. So because the substrate is going to be reacting with a nucleophile, that makes it an electrophile. So the substrate in these substitution reactions is an electrophile. The bromine is the part of the electrophile, or the substrate, that's going to detach in the course of the reaction. So this is our leaving group, which I'll abbreviate as Lg. Let's look at the mechanism for how this reaction happens. So what we saw when we saw a bromide ion attack a bromonium ion in an addition reaction was that the nucleophile attacks the carbon that has the leaving group, forms a bond to it, and the leaving group departs. And that happens all at the same time. So to draw that, we would originate an arrow, add a lone pair on the nucleophile, point to the carbon with the leaving group. That shows that the carbon in the cyanide ion is forming a bond to the carbon that has the bromine attached to it, at which point something has to leave, because that carbon that has the bromine on it cannot end up attached to 5 different things, or 5 things. So the bromine has to leave. We have to have a leaving group. So that's an SN2 reaction and results in this product. The bromine, which was the leaving group, now exists outside of the substrate as a bromide ion. Now, if this reaction, or if a reaction, not this one, if a reaction were to take place through an SN1 mechanism, let's look at a set of conditions that would favor an SN1 pathway. So we'll start with this as our substrate. Which is also going to be considered an electrophile because it's going to eventually react with a nucleophile. And then let's put this together with some water. The water is going to be the nucleophile. And so we're going to write a mechanism now. Before we do that, let me point out that the SN1 reaction always involves carbocations. So a lot of the things that you learned about how to handle carbocations when you looked at addition reactions are going to come back here. So how does this happen? So what happens in this reaction is that the leaving group leaves on its own. So the compound ionizes. It forms an ion pair. And the ion pair is a carbocation and a bromide ion. What happens next is something that you've seen before, because we've seen what happens when water and carbocations are in the same neighborhood. The water acts as a nucleophile and attacks the carbocation. That's a messed up arrow. Let's change that. There we go. So the water acts as a nucleophile, attacks the carbocation, and so you get an intermediate that looks like this, and you've seen intermediates like this before in addition reactions. So you also know that what happens next is that now the water plays the role of a Bronsted base and removes a proton from this intermediate to give you the product. Let's change our arrows up and point directly to the product, like so. Okay, so that's an SN1 mechanism. Now let's turn our attention to elimination reactions. An elimination reaction involves removing a hydrogen that's what we would call in a position that we would call beta to a leaving group or to a carbocation, and the result of that is the formation of a double bond. So the first thing to think about or to have on your radar is that all elimination reactions form pi bonds. Now in this section of material, we're going to be forming alkenes. Okay, so just one pi bond. But in other elimination reactions, you can end up forming alkynes as well. So they all form pi bonds. Now, just like the substitution reactions, an elimination can happen either through a stepwise mechanism that will also involve carbocations, and we call that E1, or through a concerted mechanism, which we call E2. So let's look at the stepwise version of this first, the E1 pathway. Let's start with this as our substrate. And once again, we're going to combine this with water. Now you may notice that this is exactly the same set of conditions that we used when we looked at the SN1 reaction. So we'll talk about that shortly. So the same first step is going to happen. The compound will ionize. And so you get a carbocation and a bromide ion. And then what happens is the following. The carbon with the positive charge we call the alpha carbon. One bond away are what are called beta carbons. In this instance, water will now act as a Bronsted base and remove a proton from one of the beta carbons. So we show that by drawing an arrow starting at the water, at the lone pair on the water, pointing to one of the beta hydrogens, and then the electrons in the beta carbon hydrogen bond move over to form the pi bond. And so we get an alkene as the result. Now let's go back to the point that I made at the beginning of this E1 discussion, where I pointed out that we're using the same substrate and the same reagent. So tert butyl bromide and water. Same example that we used for SN1. So the point that I'd like to make here is to let you know that E1 and SN1 are in competition with each other. So most of the time, when you have one of them happening, the other one is happening too. There's only going to be one case where you only get one of them followed, one of these pathways followed. We'll look at that at the end of the packet. But for the most part, E1 and SN1 are always in competition. Both of these are stepwise. So they both have stepwise reaction mechanisms, meaning they're occurring in several steps, or more than one step. And both involve carbocation intermediates. Now let's turn our attention to E2. So let's look at a different substrate. So this is going to be the concerted version of an elimination reaction, meaning that the reaction happens all at once, one step. So let's use this as our substrate. And we're going to use this as the reagent. Now you might notice when I'm drawing these reagents, so on the first page with the SN2, I gave you the example of the cyanide ion. At first I wrote it out as sodium cyanide, but then when I wanted to use it in the reaction mechanism, I omitted the sodium counterion. So you can omit the counterion because really it's a spectator. We'll talk about this a little bit more when we start looking into more depth in these reactions. But it is there. Okay, so there is a counterion. In the case of tert butoxide, that's going to be a potassium ion, but again, it's a spectator, so we're not going to worry too much about it. Okay, so in an E2 reaction, again, this is concerted, the leaving group is attached to the alpha carbon, and one carbon away from that is the beta carbon. So I'm going to draw one of the hydrogen that's attached to the beta carbon, and what happens in an E2 reaction is that a base removes that proton. So we draw an arrow starting at the base, pointing to the proton. The electrons between the beta carbon and that proton move down between the alpha and beta carbons to form the alkene. That would exceed the octet on the alpha carbon, so a pair of electrons has to move away, and that's the function of the bromine leaving group. So the bromine departs with the pair of electrons that join it to that alpha carbon. The result is an alkene. So some comments about E2. First of all, E2 and SN2 compete. And we're going to be looking in great detail into that competition, because that's probably the most important competition that you have to worry about in this packet. And so the other thing about E2 and SN2 is that they are both concerted. And you'll notice that neither one involves a carbocation. Now, what is it that you need to consider when you look at a reaction, set of reaction conditions? How do you know what you're supposed to be looking at? What do you need to focus on in order to tell whether a reaction is going to be SN1, SN2, E1, or E2? Okay, so there's a few things. Let's talk first about what you might call structural factors. That's going to come down to, is there steric hindrance in either the substrate or the reagent that you're reacting it with? So the substrate, we know already, that's going to be the thing that's undergoing the reaction. So it's going to be an organic compound that's undergoing reaction. The reagent could be wearing different hats, depending on what kind of reaction you're talking about. So the reagent, if it's a substitution reaction, we'll say SN for substitution, then we would think that think of the reagent as a nucleophile. So if it's a substitution reaction, then the reagent is playing the role of a nucleophile. But if it's an elimination, or E, reaction, then the reagent is going to act as a Bronsted base. So let's look at this idea of steric hindrance. What does steric hindrance mean? Well, we already know about steric strain. Steric strain is what happens, for example, in a conformation of a molecule where two large groups get too close to each other. Think about the eclipsed conformation, or one of the eclipsed conformations in butane, where the methyl groups are eclipsing one another. That's steric strain. So large groups getting too close, their electron clouds repel one another, that raises the energy of that conformation. So that's strain. But steric hindrance is when you have two separate things, and they're trying to react with one another, and maybe some groups on one are too close to the groups on the other, and so they repel one another instead of attracting one another, and that prevents the reaction from happening either in a timely way or in some cases at all. So let's compare what I just drew here to this guy. So we have tert butyl bromide, or T-butyl bromide. And then this one is, as you know, ethyl bromide. Now, one of the things that we're going to be doing is labeling our substrates based on the type of carbon that the leaving group is attached to. So in tert-butyl bromide, the leaving group, the bromine, is attached to a tertiary carbon, and so we can call this a tertiary substrate. Whereas in ethyl bromide, let's label that tertiary carbon there. In ethyl bromide, the bromine is attached to a carbon that's a primary carbon. And so this is a primary substrate. So this is just using the labeling notation that we learned quite a while ago now about how to classify alkyl halides. So when we look at these two structures, what we can think about is that if a nucleophile were trying to attack tert-butyl bromide, let's say, okay, so let's say that a nucleophile wants to attack the carbon and bond to the carbon that has the leaving group. It's going to have a hard time doing that because there's 3 methyl groups already attached to that carbon. And so those are bulky and they're in the way. So we would consider tert-butyl bromide an example of something that we'd call sterically hindered. By contrast, though, the same nucleophile trying to approach ethyl bromide and bond to the carbon that has the bromine so that it can replace the bromine, that's much less sterically hindered. So it doesn't have as much stuff in the way that would disallow the nucleophile from approaching that carbon close enough to form a bond to it. So ethyl bromide is not sterically hindered. So we're going to need to be able to look at compounds, and once you get the hang of this, after the first few examples, it's very easy to do. We need to look at compounds and assess how much steric hindrance is present. Now the same thing might be true in the reagent. So whether something is going to act as a nucleophile or a base, that might have something to do with how sterically hindered it is. So that brings us to our next point, the nature of the reagent. Is something going to act as a nucleophile, in which case it's going to bond to carbon? So nucleophiles, in the examples that we're going to see, will bond to carbon. Or will that reagent, is it going to be more likely to act as a Bronsted base? If it's going to act as a Bronsted base, it's going to bond to hydrogen. It's going to remove a proton from the substrate. So let me give you a pair of examples that illustrate what I mean by this. So let's use tert-butyl bromide from up above. And remember, that was an example of something we considered sterically hindered. And then we're going to combine that somehow with KOH. Now, again, the business end of KOH is the hydroxide ion. That's the thing that's going to be doing whatever kind of reacting is going to happen here, not the potassium counterion. In this case, what's going to happen is that the hydroxide ion is going to act as a Bronsted base from a beta position and give you an E2 pathway. So here, hydroxide removes a beta proton and an E2 reaction occurs. So in this instance, hydroxide is acting as a Bronsted base. But that doesn't mean that it always will. So let's look at hydroxide in the context of a different reaction, and that would be this one. So now we're going to take ethyl bromide and treat it with KOH. And again, it's the hydroxide ion that's the business end of this. The result you get here is this one, where the OH has replaced the bromine. So here, hydroxide ion attacks carbon and replaces bromine. So what happened was an SN2 reaction occurred, and the hydroxide ion acted as a nucleophile. So notice that you have the same reagent in two different situations, and it's going to do two totally different things. In the first example, we had an E2 result. In the second example, we have an SN2 result. Now in these examples, this ties back to our first idea. It has to do with the structural factors or the steric hindrance that's inherent in tert-butyl bromide, but that's not present in ethyl bromide. Now in all of these cases, or in all of these reactions, there's going to have to be a leaving group. So that's true whether it's a substitution or an elimination reaction. Part of the substrate is going to leave with the pair of electrons that bonds it to the carbon that it was attached to. The overarching idea for substitution and elimination reactions is what we said on the very first page of this, which is the weaker something is as a base, the better it is as a leaving group. So weaker bases make better leaving groups. And this is just another reminder that it's good to understand acid and base strengths. Because remember when we talked about those, I mentioned that a lot of the ideas that we were considering were going to come back in the context of other situations and other reactions. And so now we've arrived at that point. The final thing that you might consider, in some cases, you won't always have to look at this, but in cases where you do, is the solvent. So the solvent can have an effect on the reaction, specifically on the rate of the reaction. So it might slow the reaction down, or it might speed it up. It might even participate in the reaction. That's a situation called solvolysis. So we're going to learn some things about solvents and where we need to assess the solvent and consider what impact it might be having on what's going on in our reaction. So that's an overview of what we're going to do. What we're going to go into next is to just start looking at each of these reaction pathways in detail and look at the nitty-gritty of each of them.